Hello, and welcome back to our next video of the bite-size integral calculus series. And in this video, we'll be continuing our previous discussion on calculating the actual area under the curve of the curve y equals e to the power x, bounded by the intervals x equals 0 to x equals 1. And since this is a continuation video, if you have not watched the previous video, I would highly suggest you to first watch the previous video in order to get the full context of the discussion that we'll be doing in this video. So I'll start with the idea that we discussed in the last video in order to calculate the actual area under the curve of y equals e to the power x. So what we realized in order to calculate the actual area under the curve, that we'll just take those extremely thin vertical rectangular strips, and add the areas of those individual vertical, extremely thin rectangular strips in order to calculate the actual area under the curve. So for example, based on this curve y equals e to the power x, I'll take those extremely thin vertical strips and add those areas of the individual rectangular vertical strips that I have in order to calculate the actual area under the curve of y equals e to the power x. But before we start with calculating the actual area under the curve, there are two important facts that we'll be using in this video. So we'll be covering those two important facts first, and then we'll move on to calculate the actual area under the curve of y equals e to the power x from x equals 0 to x equals 1. And those two important facts are, one is the sum of the geometric series and the formula behind the sum of the geometric series. So if you don't know what a geometric series is, I'll give a brief overview of what geometric series is. So basically in the geometric series, the ratio of the two consecutive terms is always the same. So as you see in this example as well, I have the series 1 plus r square so on to r raised to power n minus 1. And you notice one thing in this case as well, that the ratio of the two consecutive terms in this case is 1 by r. If I take these two terms, the ratio is 1 by r. If I take the second and third term, the ratio is again 1 by r. So this is the geometric series when the ratio of your two consecutive terms is always the same throughout the whole series. And based on the geometric series, based on this geometric series that you have, which is denoted by 1 plus r square, so on until r raised to power n minus 1, the sum is equal to the formula that you see on the right, which is r raised to power n minus 1 divided by r minus 1, given the condition that r is not equal to 1, because if r is equal to 1, the denominator will become 0 and the sum would not exist. So this formula does not apply to r equals 1 case, but if you have a common ratio, this r is also known as the common ratio. So if you have a common ratio which is not 1, you can use this sum formula in order to calculate the sum of a geometric series. And with the first fact, we'll also use a second fact in this video, that limit x approaches to 0, e to the power x minus 1 divided by x equals 1. I'm sure most of you must have come across this limit definition before when you would have taken your first year differential calculus class in your high school or in your university. In order to prove this, you basically have to expand e to the power x, the Taylor polynomial series that you know for e to the power x, which is 1 plus x square upon 2 factorial plus x cube upon 3 factorial, so on. And if you expand e to the power x, subtract 1 from the series and divide by x, you'll see that if you take the limit of x approaches to 0, it will approximate the answer to 1. And we'll use these two important facts in order to calculate the actual area under the curve. So now we'll start with the actual area calculation. Again, the same plot will do the same process. We have divided our interval. We have divided the interval from 0 to 1 into n equal parts such that the width of each rectangle that I'm taking is 1 by n. As you can see on the screen as well, each of these parts have widths 1 by n, where my n is tending to infinity, so that I have very extremely thin vertical rectangular strips, and I just have to add the areas of those individual vertical strips in order to calculate the actual area under the curve. The same process that we discussed in the last video, the same process that we'll be doing in this video as well. Also, please note that the visualizations or the shapes that you see on the screen are magnified for simplicity. The width 1 by n is not exactly this, but would rather look like this, a very extremely thin vertical rectangular strip. But in this case, we have just magnified everything for simplicity so that it's easier to see what's going on in the actual area calculation that we would be doing. So now we'll start with the actual area approximation. And you see one more thing, that if I'll take these rectangles, of widths 1 by n each, I'll get consecutive rectangles of height e to the power 0, and then e to the power 1 by n, and then e to the power 2 by n. And based on the pattern for the height of the rectangles that I observe, I realize that I'll have to use geometric series calculation somewhere in my actual area under the curve calculations as well. So we'll start with the calculations. We'll denote the total area or the actual area under the curve of e to the power x as A, and we'll calculate the total area by taking the sum of the areas of the individual rectangles that I have. So the area of the first rectangle, the smaller rectangle that I have, is basically e to the power 0 times 1 by n, which is height times width. The second area, the area of the second rectangle, is e to the power 1 by n times 1 by n. And I can keep on following this process and adding the areas of the consecutive rectangles that will be formed in this actual area calculation until I reach the very end of my series, for which the area of the last rectangle or the tallest rectangle would be e to the power n minus 1 upon n times 1 by n. Because you see that in the last rectangle case, I have this rectangle which is basically given by e to the power n minus 1 upon n, which is already written on the screen as well. So now I'll try to simplify these series. I'll take 1 by n out because it's common in each term. So the area would become 1 by n times e to the power 0 plus e to the power 1 by n, e to the power 2 by n, so on until e to the power n minus 1 by n. That's it. And in the next process, I'll further simplify these series. I can write e to the power 0 as 1, right? So I'll write 1 by n times 1 plus e to the power 1 by n plus e to the power 2 by n, so on until e to the power n minus 1 by n. And this is exactly the place where we will use the formula for the sum of the geometric series. Because I noticed one thing in this series, that it closely resembles the series that I discussed in the first half of the video as well, which was 1 plus r square, so on until r raised to power n minus 1, right? Where my r is basically e to the power 1 by n. Or in other words, if I have to frame it in another way, I see that the ratio of the consecutive terms is always the same, which is always e to the power 1 by n. So if I take the ratio of these two terms, and all the consecutive terms, my common ratio is always the same. So that is why it gives me an idea that I have to use the sum for the geometric series. And since I already know that the sum of my geometric series is basically r raised to power n minus 1 upon r minus 1, and in this case, my r is e to the power 1 by n, so I'll just substitute all those values in it. So my actual area will become e to the power 1 by n times n minus 1 upon e to the power 1 by n minus 1. And further simplifying this down, I'll get 1 by n e minus 1 e to the power 1 by n minus 1, because e to the power 1 by n times n becomes e to the power 1, which is indeed e. So now I have this thing. I can take e minus 1 out because e minus 1 is basically a constant, and the rest part becomes 1 by n upon e raised to power 1 by n minus 1. Now we have simplified all the calculations to the maximum extent that we could, and this is the exact time where we will take the limits for n, because we discussed in the first half of the video as well, while taking the sum of the individual areas of those extremely thin vertical rectangular strips, we will assume n to go to infinity so that the area approximation or the area calculation becomes exactly equal to the actual area under the curve. Because if n approaches infinity, my width of those individual rectangles become very close to 0, so that I have those individual vertical thin strips, and I can add all those vertical thin strips up in order to calculate the actual area under the curve. So that is why at this point of time, for the area calculation, since e minus 1 is a constant, it will remain in the front, and I'll take the limit of this part, the limit for which my n will go to infinity. And if I'll calculate this expression, I'll basically get my actual area under the curve of e to the power x, bounded by the intervals x equals 0 and x equals 1. And this is the point where we'll use the second fact that we discussed in the first half of the video. The second fact was, if I have a limit of e to the power x minus 1 upon x, where my x is tending to 0, the limit is always equal to 1. And we see that it's very similar. This limit is very similar to the limit that we discussed in the first half of the video. Instead of 1 by n, I just need an x in place of 1 by n. And instead of n tending to infinity, I want x tends to 0. And we also know how to manipulate limits because of the first year calculus courses that we took. So basically what I'll do in this case is, I'll take 1 by n as x such that when my n tends to infinity, my x tends to 0 in this case, right? Because in this case, if my n becomes very large, my denominator becomes very large, and that indeed makes x to approach to 0, right? And now what I'll basically do is, I'll change every occurrence of 1 by n, and we'll see how it turns out. So now my area becomes e minus 1, which is always in the front because it's a constant. My limit will become x tends to 0, 1 by n will be changed to x, e to the power 1 by n will be changed to e to the power x, and minus 1 will remain the same. And you see this thing, that this is exactly equal to this. It's basically the reciprocal of each other, but the limit is exactly the same, right? And I know based on the definition of this limit that I also proved in the video, that this limit will also be equal to 1. So following this calculation, my actual area under the curve for y equals e to the power x, bounded by the intervals x equals 0 to x equals 1, turns out to be e minus 1, which is equal to 1.718, and this is exactly equal to the actual area under the curve for e to the power x, bounded by those intervals from x equals 0 to x equals 1. And you can follow the same process in order to calculate the actual area under the curve for any complex function that you would like to know. You can also try this same approach for y equals x, for y equals x square, x cube, or even ln x, and you can follow the same approach in order to calculate the actual area under the curve of those functions without using any existing formulas for integration and just relying on the fundamentals of the calculations of area under the curve. So that was it for today's video. I hope you found it interesting. Please follow the channel for more updates. And thank you so much for watching. Stay tuned. Bye bye.